All right, here we are. We're going to talk about the binomial theorem and what it's telling us. Remember, the binomial theorem is a way to help us do calculations like this in a very, very quick manner. And the way it works is pretty straightforward. I'm going to jump to number 5 because I think we did some of the work that was leading us to this pattern that the coefficients of the terms in my answers were always following the pattern of the Pascal triangle numbers or the combinations that we get. So I'm going to jump to number 5 because I want to show you how easy you can multiply this out without actually multiplying things out. So here's what we do. We look at the power. Let me use this color. We look at the power and we go either to Pascal's triangle to the 5th row because my power was 5. And I'm going to use and write. Oh, there you go. Oh, almost. There you go. I'm going to use and I'm going to write the pattern of numbers here in the 5th row. Why the 5th row? Because this was to the 5th power. And so if I go back to my sheet here, this is the 5th power. So I'm going to write those numbers that were in the 5th row of Pascal's triangle. But I'm going to leave space. So I'm going to write 1 and I'm going to leave space. 5. Oh, my Lanta. My pen. I'll switch back to my older pen. 5. And I believe the next one was 10. And I believe the next one was 10. And then I think the next one was 5. And then the last number was 1. So this should be the row of numbers in Pascal's triangle on the 5th row. Why the 5th row? Because these were this was to the 5th power. Great. Now here's where it gets even easier. I'm going to take my first term and I'm going to take it to the 5th power. And I'm going to write it in the first term, x to the 5th. In every term that comes after that, it's going to drop down 1 power. So then the next one's going to be x to the 4th. And then the next one's going to be x to the 3rd. And then the next one's going to be x to the 2nd, x to the 1st. Technically, the last one should be x to the 0, but x to the 0 means that there's no x, so I'm not going to even write it. How did I do that? Because my first term was x, and they're going to start with the power of the binomial and then decrease in exponent power all the way down to 0. Pretty straightforward. Great. Now let's do this. Now I'm going to take the second term and I'm going to take it to the 5th power, but I'm not going to write it at the beginning. I'm going to write it at the end, y to the 5th. And then the one before, y to the 4th, y to the 3rd, y to the 2nd, y to the 1st, and this should be y to the 0, but y to the 0 means there's no y, so I'm not even going to write it. And if you connect these terms with addition, you just found the answer that you would get if you multiplied x plus y times x plus y times x plus y times x plus y times x plus y 5 times. This would be the answer that you got. This is what the binomial theorem allows us to do. It allows us to multiply binomials however many times you want, whether it's 5 times or whether it's 6 times. Remember, what this says, or maybe I should say, what this means is x plus y times x plus y times x plus y 6 times. That's a lot of multiplication I would have to do, and I'm kind of lazy and really don't have time to do that, right? 1, 2, 3, 4, 5, 6. X plus y multiplied 6 times. That's a lot of work. But what the binomial theorem says is, if you know Pascal's triangle, or if you know the combinations, and you do 6C0, that's going to be the first number. 6C1, that's going to be the second number. 6C2, that's going to be the third number, and so on, you can get the answer to this binomial expansion fairly quickly. Now, If you drew Pascal's triangle, you should have the row for the 6 power of 6. So I'm going to sneak a peek over here and go back to Pascal's triangle and see if I can use the information we already have. I'm talking about this. I'm going to use those numbers, 1, 6, 15, 20. Again, notice, I just need to know the first 4, because then after that, they go backwards and they repeat. So 1, 6, 15, 20, and then it's 6, 15, 6, 1. So 1, 6, 15, 20. Great. So I come back over here. What am I trying to do? I'm trying to multiply all these green x plus y's, but I don't have time. So I'm going to say 1, 6, 15, 20, and then go backwards, 15, 6, and 1. 1, 2, 3, 4, 5, 6, 7. Notice, I have 7 terms, even though this is to the 6th power. Over here, I have 1, 2, 3, 4, 5, 6 things that I'm adding, even though it's to the 5th power. So the number of terms is always 1 more than the exponent value. By the end of this, I'm going to have 1, 2, 3, 4, 5, 6, 7 terms, because my exponent is to the 6th power. Great. How do I start? Well, x to the 6th, and then x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and x to the 0. No x. And then I start backwards. Take the 2nd term to the 6th power, but start from the end and work your way forward by dropping 1 degree or 1 exponent power every time. To the 1st, this should be y to the 0, so I'm not going to write any y, and then I'm going to connect those with a plus sign. This is the answer. I don't need to multiply x plus y times x plus y times x, all this. I don't need to do that. The answer is right here. And we're done. This is the binomial theorem. The binomial theorem. Binomial means 2 terms, x and y. I'm adding those 2 things. It's a theorem because it says if I'm multiplying binomials, then I can use this pattern to write out the answer. And I don't need to actually multiply them out. Now again, this only works if I'm multiplying the same binomial, 6 times. But if I am, then boom, I'm done. I need you to notice a couple of things before we go on to the next video. I need you to notice that if you add the exponents, they should add to the original power. Add 3 and 2, I get 5. Add 2 and 3, I get 5. Add 1 and 4, you get 5. Or on this example, add 4 and 2, you get 6. Add 3 and 3, you get 6. Add 2 and 4, you get 6. Add 1 and 5, because there's a 1 here, and I get 6. And even the one at the end, 6, oh yeah, that matches 6. That's how you can check yourself to see if you're doing it right. Are the exponents for each of these terms adding up to the big exponent that I started with? We're going to come back in the last video. We'll do a couple of examples, and then we'll be good to go with this binomial theorem shortcut. That's what it is. The binomial theorem is a shortcut to multiplying binomials when they're taken to a big power.